E is the electron charge, 1.602 times 10 power minus 19 coulombs. Charge is the electron charge is the 1.60 time 602 times 10 power minus 19 coulombs. Like charge will be existing, like let us say Q1 is equals to plus or minus 1e or plus or minus 2e or plus or minus 3e or plus or minus 4e, okay, or 5e, like that, but it will not be like 1.5 or 1.33 like that. Okay, so charge is always quantized. Suppose I'm saying 1 coulomb charge means 1 coulomb charge means, so let us say 1 coulomb charge means like 1 coulomb is equals to plus or minus 1 times n times, n is the number of electrons, E is the charge of the electron, 1.6 times 10 power minus 19 coulombs, right?
Yes, sir.
So n is equals to 1 by 1.6 into 10 power minus 19. Okay. If you do that, its value is around 6.24 times 10 power 18. Okay. That means in 1 coulomb charge, how many number of electrons are there means 6.24 times, roughly I'm saying it is rough value, 6.24 times 10 power 18 electrons. So 1 coulomb charge means 6.24 into 10 power 18 electrons charge. That is what 1 coulomb charge. Okay. So suppose if I take Coulomb's law, if I discuss about the Coulomb's law, suppose if you have the like charges, like if I have a positive charge and if I have another positive charge, okay, so it is Q1 and it is Q2. If I have both the positive charge, that means like charges, they will repel each other. If I have the both negative charge also, they will repel each other. If I have one positive charge and one negative charge, they will attract each other, right?
Yes, sir.
They will attract each other. You would like to know the strength of interaction between the charges. So then Coulomb's law is useful. Coulomb's law. Basically, Coulomb's law is valid only for the point charges. Point charges. Point charges. Again, a question comes from the student mind that what is meant by point charge? Okay, suppose if I have a charge like this, if I have a charge like this, and if I place the charge, another charge like this, Q naught, it will interact. If I place over here, it will interact. If I place over here, it will interact. But if I go beyond this point, it doesn't interact. That means up to certain distance, it will interact. That means the region about which, the region around surrounding to which, it can interact the other charges. Okay. So when you compare this distance, when you compare this interacting distance, let us say X, and when you compare this finite size of this charge, let us say small d. Okay, this X is much larger than small d. Okay, then you can say that it is a point charge. The dimension of the charge is very small when compared to the its influencing distance of another charge. Are you getting my point?
Yes, sir.
So that is called point charge. Suppose if I have the 2 point charges, let us say Q1 and Q2, these are the 2 point charges. These 2 point charges are being separated by a distance, let us say center to center distance is smaller. Then the force of interaction between them, the magnitude of the force of the interaction between them, F is proportional to magnitude of the charges, product of their charges, and F is inversely proportional to the square of the distance between them. Square of the distance between them. So then F is equals to some constant you need to place, right, in order to remove that proportionality.
Yes, sir.
If I remove the proportionality, I am placing the Coulomb's constant Ke into Q1 into Q2 Q1 into Q2 magnitude by R square. I'm strictly saying you need to take the magnitude of the product of the charges. You cannot take the arbitrarily like Q1 into Q2. Okay. So magnitude of the product of their charges and inversely proportional to the square of the distance between them. Okay. And this constant KE is equals to 1 by epsilon naught. So its value is 9 into 10 power 9. 9 into 10 power 9. Its value, KE value is 9 into 10 power 9. I will tell you unit, how to find out the unit of KE.
Yes.
KE is what?
K is the
Proportionality
Coulomb's
constant, right?
constant, right?
Yeah, yeah, Coulomb's constant. Its value is 9 into 10 power 9 Newton meter squared Coulomb squared. This is the unit. Then how do we remember? So Ke is equals to, if you can write the subject like this, F into R squared by magnitude of Q1 and Q2, right?
Yes, sir.
Am I correct? So what
Yes,
is
sir.
the unit of force? Force unit is Newton, distance unit is meter, by charge unit is Coulomb, and the another charge unit is Coulomb. So Newton meter squared by Coulomb squared is the unit for this Ke. And one more constant is coming, that is epsilon naught. Epsilon naught is what? Permittivity.
Okay, sir.
Permittivity of the free space. Value is 8.85 times 10 power times 10 power minus 12. That is the permittivity unit. Then you can write the unit of permittivity. Okay. What is that unit of permittivity? That is the Coulomb squared per Newton meter squared, right? Coulomb square per Newton meter squared. So that, so the again in the first year that you have read in the 11th grade, you have read that force is a vector quantity, right?
Yes, sir.
Force is a vector quantity. That means if you have taken the two positive charges like this, if you have taken the two positive charges like this, plus Q1, and it is Q2 plus Q2 plus Q1 and plus Q2, there is a repulsive force between them. So that means there is a repulsive force between them like this. Okay. Suppose if you take the plus Q1 and minus Q2 like this, minus Q2 like this, there will be an attractive force, right? There will be an attractive force. There will be an attractive force like this. So force is a vector quantity. So F bar is Ke into Q1 into Q2 magnitude by R squared into R cap. R cap is the unit vector along the force direction. So this is the R cap direction, or this is the R cap direction. Okay, that is the Coulomb's law. So do you understand what I told you?
Yes,
So
sir.
what is Coulomb's law? Coulomb's law is valid for the point charges, right?
Yes, sir.
Coulomb's law is valid for the point charges. If I take the 2 point charges Q1 and Q2, the force of interaction, I'm not saying force of attraction or force of repulsion, both are the part of the force of interaction. So whenever you separate the two charges with a certain distance r, there is a force of interaction between them. So that force of interaction is proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. If I rewrite this equation, okay, in order to remove the
Yes, sir.
proportionality, I need to place a constant that is called the proportionality constant, or you can call it as the Coulomb's constant.
Okay, sir.
Coulomb's constant. So Coulomb's constant value is 9 into 10 power 9 Newton meter square and Coulomb square. Newton meter square and Coulomb square. So Ke is equals to I have written like how I have written the unit for KE. In order to remember that, so what I have written is KE is equals to F into R square by magnitude of Q1 into Q2. So force unit is Newton and distance unit is meter square. So Newton meter squared by Coulomb square. Okay,
Yes,
where
sir.
epsilon naught is the permittivity of the free space. Again, a term coming, important term is called free space. Free space means there is nothing. Okay, suppose you take a room in which what will be present generally, a gas particles will be present, right?
Yes,
Oxygen
sir.
molecules, nitrogen, carbon dioxide, all will be present. Mixture of dust particles will be present. If you suck out all these particles, then it will be like empty one. It will be
Yes,
like
sir.
empty one. This is called free space. So there will be nothing present in that room. That is called empty space, or you can say free space. The free space generally available when you are going above the earth surface, in between the planets, you won't get anything atmosphere, right?
Yes, sir.
So there you will be getting very free space. Or in order to have the free space, what I told you is there is a simple way to suck out all the gases or the all the dust particles from the room. You will be getting the free space. So in this free space, this is the formula that is generally used for this. Okay, ke is equal f is equals to ke into magnitude of q1 into q2 by r square. But what I am doing is i'm not I'm not placing those two charges. I am placing those charges in the in a medium, let us say silicon medium. Okay, I'm placing in a silicon medium. So in that case, the Coulomb's law can be written as this is the silicon medium. Silicon medium. So silicon medium, I'm placing I think in the silicon crystal, you need to place Q1 and Q2. In that case, the Coulomb's law is equals to Ke into Q1 into Q2 by Q1 into Q2 by R squared. Here, in this case, Ke is equals to, when in the presence of the medium, you have to write one epsilon naught. Epsilon is the permittivity of the silicon medium. Permittivity of the silicon medium. You cannot write like epsilon naught. So now Ke is this. What I can write it is F is equals to F is the, in the presence of the medium, we will represent with F prime. So this is the silicon medium is equals to 1 by 4 pi epsilon, 1 by 4 pi, not epsilon, epsilon into Q1 into Q2 by R squared, right?
Yes, sir.
Yeah. So this is what the difference. And there is another constant is called the K. Ke is called the epsilon R. Epsilon R is the relative permittivity. Relative permittivity of the free space. Permittivity of the medium to the permittivity of the free space. That is called, that is also called the dielectric constant. Dielectric constant. Dielectric constant. Okay. So did you
So what
understand
is called as
how do we
dielectric
differentiate it?
constant?
Yeah, dielectric constant is called the permittivity of the medium to the permittivity of the free space.
Oh, okay,
Okay.
sir. Yeah.
It is the ratio. Permittivity of the medium to the permittivity of the free space. That is called the dielectric constant epsilon r, right? That is called
Yes,
dielectric
sir.
constant. Okay.
Okay, sir.
So next, Okay. So we differentiated the Coulomb's law in free space, and from the when you place the when you place the two charges in a free space, this is the Coulomb's law. When you place the two charges in a medium, okay, in a medium like silicon, the Coulomb's law is like this. Only thing is you need to replace the epsilon with the epsilon naught with the epsilon, right?
Yes, sir.
Right. Now, what is meant by an electric field? That is the next question. So electric field. Okay. Now, so suppose if I take the charge Q, okay, here, and it will attract the another charge, right? It will attract the another charge surrounding to it, right?
Yes,
Or
sir.
it will repel, right? Yeah. What I'm doing is I'm placing a charge Q naught over here, which is at a distance, Q naught is the positive charge. Okay. This is called the test charge. People use it to call it as the test charge. Okay. I
Okay,
need
sir.
to test the uh, for the testing purpose. So Q is the charge, and at a distance R, I have taken the another charge. According to Coulomb's law, if it is the free space, what is the electric force magnitude? F is equals to Ke into capital Q into small q naught by R squared. Am I correct?
Yes, sir.
This is the force. Okay. So force of interaction. Force of interaction between Q and Q naught. Okay. Okay. Now, so if I divide the F with Q naught, what I will be getting expression is Ke into Q by R squared. Am I correct?
Yes, sir.
This ratio is called the electric field intensity. Okay. This is called the E is equals to F by Q naught. F by Q naught. Okay. This is called the electric field intensity. Electric field intensity. Electric field intensity is the amount of the force per unit test charge is called the electric field intensity. Again, there is an electric field is a vector quantity. Electric field is a vector quantity. Then again, you need to indicate the direction because it is a vector quantity. It is Q naught, it is Q, and it is at a distance R. Now, these two are the positive charges. Hence, the force direction will be like this only, right?
Yes, sir.
So E bar is equals to K into Q by R squared into R cap. This is the electric field due to a point charge. Electric field due to a point charge. Electric field due to a point charge. So now, electric field due to a point charge depends on what amount of the charge. Suppose if you take the 2 points over here, this is the test Q charge. If I take the 1 point over here, and if I take the P point and if I take the Q point like this is RP and this is RQ. So where you will be getting the more electric field?
P and point Q, right?
Yes, point R, right? If distance is more, electric field strength is less, right?
Yes, sir.
If distance is more, electric field strength is less. Okay. So
sir.
hence P point is more, having electric field strength is more than the EQ. Okay, EQ point.
Okay,
Okay.
sir.
And here why I have used the test charge Q naught? Q naught is the only for the testing purpose. So how much amount of the force is present? Okay.
Hmm.
So only for that purpose only I have written. And what is the unit for the electric field? That is important. Unit is force unit is Newton, right? Force
Yes,
unit
sir.
is Newton and charge unit is Coulomb. So Newton per Coulomb is the unit for the electric field. Okay. So electric field is the electric force magnitude of the electric force per unit test charge. That is called electric field intensity. So that means how,
Magnitude of, so can you repeat it? Magnitude of the,
so see, electric field intensity can be defined as amount of the electric force per unit test charge.
okay, sir.
Amount of the electric force per unit test charge. That means it is like a strength. With what strength it will interact. Okay, because F bar and E bar comma F bar are in the same direction. Whatever be the F bar direction, you will be having the same direction as the E bar. Did you understand my point?
Yes, sir.
Yeah. So force acting per unit test charge electric field intensity. Force, electric force acting per unit charge is called electric field intensity. Electric field intensity. Okay, that is the
Yes,
electric
sir.
field intensity. What is the unit for this? What is the unit of the electric field
It is
intensity?
Newton per coulomb, right?
Yeah, Newton per Coulomb. Okay, and this the finding of the electric field due to different charge distributions is important. Suppose I think this is the Q and this is the point P. At this point, electric field. You will be writing like K into Q by R squared, right?
Yes,
Yeah,
sir.
like this. Suppose if I have a continuous charge distribution, this is a point charge, right? This
Yes,
is a
sir.
point charge. This is a point charge. Suppose if I have a charge like this, okay, charge is distributed uniformly. Charge is distributed uniformly, and I would like to know the electric field at this point. Electric field at this point. In this case, it is very difficult, right?
Yes, sir.
Because if I have the point charge, then I can easily do with the help of this formula. E bar is equals to Ke into Q by R square into R cap. Okay, R cap is the unit vector, which represents the direction of E bar, right?
Yes, sir.
R cap is the direction of E bar. Okay, normally E bar direction is away from this point. Suppose if you have a charge like this, at this point electric field is away from it. Always from the positive charge away from the electric field. Okay, right. Now my question is, for a continuous charge distribution, for a continuous charge distribution, let us say there is a it is a full of charges like this. That means it is covering the very small charges, right?
Yes, sir.
Like this. Yeah. So what I am doing is I will do some elemental charge. I will calculate the electric field due to elemental charge dq first. Dq is equals to, this dq is at a distance, let us say r1. Okay, so this is a dq1. What I will be doing is I'm dividing this entire charge into infinitesimal elements. That means small charge elements, piecewise elements I'm doing. So one such element I'm taking. So I'm calculating the, at this point P, electric field due to this charge. I'm writing from that E1 is equals to KE into dq1 by R1 squared. Similarly, E2 is equals to KE into dq2 by R2 squared. Similarly, E3 is equals to KE into dq3 by R3 square. Can I write it like this?
Yes, sir.
So dq1 is like this, dq2 is like this, dq3 is like this, and so on. Okay. So if I write the total electric field, E total is equals to E1 bar plus E2 bar plus E3 bar and so on. Okay, that means KE into dq1 by R1 squared plus KE into dq2 by R2 squared plus KE into dq3 by R3 squared plus and so on. Okay, we can
Yes.
write this like this: some KE into sigma over I runs from 1 to n dqi by ri whole squared. Can I write it like this?
Yes, sir.
Okay, if I substitute I is equals to 1, I'll be getting the first term. If I substitute I is equals to 2, I'll be getting the second term. If I substitute I is equals to 3, I'll be getting the third term. If I substitute n, then I'll be getting the nth term. That means a different the electric field due to different charges I'm getting. Okay, so there are n such number of elements, right? So the total electric field in the total E total in the limiting value, if you take limit delta q or dq tends to 0, E total, then what you will be getting is K into the summation is being replaced with the powerful tool is called the integration. Rather than adding all the terms, what I'm doing is I'm using the simple formula integration. So with the help of the integration, E total can be calculated. E total due to the continuous charge can be obtained by, so K into integral dq by r squared. Okay, this is the formula for electric field due to continuous charge distribution.
Okay, sir.
I think I'll be repeating what we did.
Sir,
So
Prabhakar,
electric, yes, sir.
Yeah, sir, the session will be closed automatically within 2 minutes, sir. So we have 3 minutes only.
Yeah, right. Thank you.
Okay.
Yeah. So I'll be just revising the things what we have done.
Sure, sir.
So
Okay, sir.
electric field and electric force are in the same direction. Electric force per unit test charge is called the electric field intensity. Now, electric field due to a point charge, it is very easy to write K into Q by R square into R cap.
Yes.
But if you come across the, like, suppose you have a ring like this, and among the ring, there is a charge. Upon the ring, there is a charge. If you would like to calculate the electric field, then that point charge equation will not be valid for you. Or if you take a charged disk, CD disk, if you are supposed to calculate the electric field at this point, then that formula is not helpful for you. Okay, some extent it will be helpful, but it will not be extent for the continuous objects. So in order to go for the continuous objects, what we are doing is continuous charge distribution object. We are doing like in the form of point charges. Okay, so we are dividing this entire charge q into dq1, dq2, dq3, and so on, dqn, like that. So what I'm doing is at this point, I'm finding the electric field due to dq1, and again I'm finding the electric field due to dq2, and finding the electric field due to dq3, and I'm adding all those electric fields so that I'll be getting the total electric field. This total electric field can be write like this, and rather than adding all the things, you can use the summation with the help of the suitable symbols like this, dqi by ri squared. And then the total electric field when the dq tends to 0, that means if it becomes the point charge like this, the size of the dq is tending to be very, very small, then this summation can be replaced with the integration. Summation can be replaced with the integration. So summation can be replaced with the integration, so that I can write it for the dq by r square. This is the very, very important formula for the finding of the electric fields due to different charge configurations. So what we did,